Hello, in this video we're going to step collisions up a notch by having these balls here moving in 2 dimensions. So we're moving around on a horizontal table rather than just going in a straight line. We're still doing exactly the same stuff, we just got to do more of it. There's no actual theoretical or conceptual difference to having collisions in 1 dimension. We just need to be very, very careful with our algebra on this, because that's the biggest threat to us actually being able to get to the end of the problem with the right answer. Right, let's see if there's anything in the picture that isn't in the picture that is in the text. Smooth spherical ball A, that's the one at the bottom, moving at speed u, so I've marked that. In a straight line on a smooth horizontal table, hits an identical ball B at rest on the table. Just before the collision, the direction of motion of A is parallel to a fixed smooth vertical wall. Yes, excellent, they've marked all that. Instant of collision, the line of centres of A and B makes an angle of 60 degrees, so they've done that as well. So we've got all of that. They've given us a coefficient of restitution being E. Show that the speed of B immediately after the collision is a quarter of u times 1 plus E. And find, in terms of u and e, the components of the velocity of A parallel and perpendicular to the line of centres immediately after the collision. Right, okay. So let's get at the moment we're working along line of centre and perpendicular to line of centres. So let's mark these things out then. So for our for A, when we start off, we want to switch this u to being in different into its component. So if that's our u, then we've got the component along line of centres and the component perpendicular to line of centres. Where's our angle in all of this? That is our 60 degrees at the top. So we can say that this component going here is going to be a u sine 30, so that's u over 2, and we got a u cos 30, which is u sine 30 is that one, and u cos 30 is the component here, so that's a u root 3 over 2. That's our components for A. That's before the collision. And then after the collision, because B is just not moving, so I won't bother putting that one on. So this is before. And now let's go to after. So after for A, this wouldn't have changed because the collision hasn't happened in that direction. So that's staying at u root 3 over 2. But we don't know what's happening in this direction. It's changed from u over 2 to some unknown, which we're going to call x. And so that's for A again. And then for B, well, it's not going to be moving at all in the perpendicular to line of centres. It's just going to move parallel to line of centres, and let's call that y. Excellent. So we can now do our 2 things that we do in collisions. We've got conservation of momentum, and we could do that in any of these directions. So let's go with a direction where everything's happening. And because these are identical balls, we can leave mass out altogether. So u over 2 is equal to x plus y. That's our conservation of momentum along the line of centres. Then we can do our coefficient of restitution, and that is going to say that our speed of approach, which is u over 2, multiplied by the coefficient of restitution e, is going to be equal to the speed of separation, which is the thing in the front minus the thing at the back, so y minus x. Now we just need to solve these simultaneously, and then we're fine. So u over 2 minus y, because that's x, is going to be equal to y minus ue over 2. So 2y is equal to, let's factorise this as we go along, u over 2 times 1 plus e is equal to 2y. So to save a bit of space, let's just change that into a 4. Get rid of that 2. I think that's the thing they asked for, isn't it? Yeah, that's our speed of b after the collision. So we've already shown that bit. So that's fine. And then we've got to do the same for x. Or we could just plug that y. Let's plug that y into one of them. So x is equal to y. So that's u over 4. I'm going to expand it out because we're going to need to. ue over 4 minus e or ue over 2. And that is going to give us, so we've got minus, that's just going to disappear and give us a minus sign there. So we've got a u over 4, 1 minus e. So that's given us the components of A for parallel and perpendicular. So we've done that first part of the question, just paying careful attention to all of our components here of velocity. All right, now for the second part, we got subsequently B collides with the wall. After colliding with a wall, the direction of motion of B is parallel to the direction of motion of A after its collision with B. Okie dokie. Let's do all of this bit in blue. So that's going to come off at some angle there, which is matching. They're going to be parallel lines, so they're matching direction. So the components of their velocity, they're going to be the same. The thing that's going to be annoying about this is we've done all of the first bit along the line of centres and perpendicular to line of centres, because that's where the collision is happening. Now the collision is happening at the wall, so we're going to have to switch to looking at perpendicular and parallel to the wall on all of this. So we're going to want to now redraw these after pictures in order to get perpendicular and parallel to the wall. So let's look at what's going on with A then. So this is our setup here. This thing here is A after the collision. Now we're going to have to rotate all of this round to look at our perpendicular and our parallel directions. Well, parallels probably, well, actually, they're both going to be fine, I think. So we need to make sure we've got our angles correct on all of this. That was 30 degrees in there. So we've got x cos 30. Yeah, so that's x root 3 over 2. And then we're taking off u cos 60 on all of this. So we can take away, u root 3 over 2 cos 60. So u root 3 over 4 is what we've got on that. That's actually direction upwards. So let's change that arrow. I know it's moving downwards, so it's going to end up being a negative of that because it's going in if we're looking downwards. And then parallel to the wall, we've now got x sine 30, so that's x over 2, plus, what angle did we have on all of this? That's 30 degrees, isn't it? This one's 30 degrees as well. Both of these are 30 degrees in here. So u root 3 over 2 cos 30. So that's going to be 3/4 of u. 3u over 4. Okay. Okay, I haven't put in x yet, but we know what x is. X is u over 4 times 1 minus e. But I don't want to clutter up the screen. And then for B, at least we've only got one thing that we're doing here with B. So we've got moving towards the wall, we've got y cos 30. That's right, isn't it? Yeah, y root 3 over 2. And then moving parallel to the wall, we've got y sine 30, so y over 2. So this is then, but we need to look at then after it's hit the wall. After it's hit the wall, so this is before it hits the wall. So afterwards, this is now going to change. So this is, so let's go after hitting wall, after wall, and let's switch these top ones to be down arrows. So after the wall, that down arrow is going to be u root 3 over 4 minus x root 3 over 2. That's just flipping the sign on it, and that is still what we know it to be, x over 2 plus 3u over 4. That doesn't change for B because the collision happens in the opposite direction. And now that down arrow is going to be minus whatever the coefficient of restitution that we're looking for. So we've already used E, so let's go for F. It's the next one along. Minus Fy root 3 over 2. So if these are parallel, we can divide these components and they should be the same. That's how the vectors work, isn't it? So yeah, we can get rid of, let's get these all over 4, because we're going to have a lot of things that can cancel then over here. We can forget about those fractions. So let's divide the y components first of all. So if we divide, we've got minus Fy root 3 over 2, and then we divide it by y over 2. Well, we're getting rid of that y over 2. So we've got minus F root 3 has got to be equal to, what have I got? What have I got? Oh, it's not minus. That minus, I've flipped the sign as well of the arrow, so that minus has gone away because we are looking in that direction. I already did it for the, in the same way as I flipped it for the A component, flipped the sign by when I changed the arrow. Well, I've changed the arrow for B as well, so I don't need that minus sign. So we've got F root 3, that's dividing the top one by the bottom one, is going to be u root 3 minus 2x root 3 divided by 2x plus 3u. Wowzers. Well, this is going to be fun to put together. So x is u over 4 1 minus e. Oh, good grief. Right, so that is, well, we can say it's u. Well, we can figure out about the u, get rid of all of the u's, because there's a u in the x's as well. We can get rid of the 4's and the 2's by multiplying all these other ones by 2. So make that a 2 and make that a 6. And then the x is now just a 1 minus e on it. So that's a 1 minus e. And then that is a 1 minus e. So that's put everything in place there. We can divide by the root 3's. Oh, this has really dropped out, hasn't it? So we've got 2 minus 1 minus e divided by 1 minus e plus 6, which is equal to, so 2 minus 1 is 1, minus minus e is plus e, divided by 1 plus 6 minus e. Oh, there you go. What do you know? It's come out of what we want. So, okay, that time worked out. You see there's a lot of algebra here, and it's very easy to just make one little mistake. I mean, I nearly went too far by leaving this minus sign in when I flipped the arrow here. Fortunately, I spotted it just before I started getting into the last bit of algebra. But there's so many steps that you have to take here, flipping between the different directions, rotating your frame of reference from line of centers. So yeah, just be very careful when you're drawing these things out. I've had to squeeze it on the screen here. So you might want to use a little bit more space when you're drawing these diagrams and you're flipping, you know, whenever you're doing a rotation, because that's the thing with collisions. You're always, or pretty much always, there might be some exceptions, but most of the time you're wanting to align your components of your vectors along the line of the collision and then perpendicular to the collision. So as soon as they start doing this, where the first collision is that way and the second one is that way, then we start having to be very careful with our trig. Fortunately, they've given us 60 degrees and a 30 degrees all the way through it, so it does make things simpler. But yeah, this is not an easy question, but you should be able to see, looking back on it, that the problems with it are nothing to do with a collision. You know, all we've done for our collision stuff is a conservation of momentum and a coefficient of restitution. Well, they're really easy to do. Conceptually, this was straightforward. It's the maths that is the problem on this. I mean, this is probably a nice one, really, where you could set this up. Maybe I'll do this in another video of actually coding this up, because this would be quite nice in code when you've got to make so many steps through your vector algebra. Automating all of this certainly would be interesting. So yeah, this would be a nice one to put as a coding exercise. But still, it's nice to look at something pretty complicated when it comes to the mathematics of collisions, at least before we get to university.